Really nice to see some familiar faces and lots of new ones. That's great. Right. Okay. Hello, Abaid. Yeah, very well, thank you. Right. Hello, Mia. Familiar faces. Venkat. I believe I marked your paper recently. Right. And everyone else. Hello. We'll start in 2 minutes. Um, while we haven't started, how difficult did you find? Sorry, have you started physics, and how many problems have you managed to do from physics? Can you just type in a number? How many problems have you already managed to do? 4, 6, brilliant. 4. Okay. 2. Okay. Am I correct in thinking that you found physics more difficult than maths? Absolutely. Well, okay, you can blame me because I, I'm the main author of physics, so I've written the physics assignment. Um, the math assignment was written by a different teacher. I was proofreading and adding stuff to it. Okay, you can blame me for the difficult physics, but hopefully today I can I will explain a lot of very similar problems and hopefully get you into the thinking frame of reference that you need to get into to actually solve these. Okay, so let's get started. I've prepared 8 problems for you. Um, I will share the link uh, with the whiteboard. Just not to do the same mistake and can view. Okay, they don't give you editing capabilities. So here's the whiteboard I'm going to use today, and for every okay, for every webinar. So you should see my screen. If you don't, let me know. Otherwise, I assume you can see my screen. So circular motion problem 1. So I've got 8 problems for you today, as usual. We will have this. So for those who are new, we'll have this webinar every week. They will alternate physics, maths, physics, maths, physics, maths. Sometimes if the physics assignment is particularly difficult, we do 2 physics. If the maths is more difficult, we do 2 maths in a row. but we try to balance it. So basically, every other week you will have a physics webinar and a maths webinar. Webinars will be on Thursday um, and the normal time is 6 o'clock. So for those of you who are new to COMPOS, you will, apart from the webinar, you will also have a tutorial with your tutor, but this is after you get accepted to the program. If you don't get accepted, you can still attend the webinars. You're welcome to come in and join. You're welcome to download the assignments, give them a go, and attend my webinars. Sometimes we will have guest lecturers for the webinar. So welcome everyone. Welcome to COMPOS. This is the second year of COMPOS. We are quite proud of it, and let's get started. Right. So circular motion, and the first question: find the linear speed, angular speed, acceleration of points on the surface of the Earth at a latitude of phi equals 60 degrees. So basically, if this is planet Earth, and 60 degrees, it's slightly a bit further north than London, 60 degrees. I think roughly Edinburgh-ish, 60 degrees. So somewhere here, the point of interest, which is rotating with the planet anticlockwise, and we need to find the linear speed, the angular speed, and the acceleration of this point. Well, we'll start with the easiest. How do you know if you are accepted or not? You will get an email basically after your work is marked. You'll get a grade, and then when we decide on the minimum boundary for the grades to get in, we will send you emails if you are accepted or not. If you are accepted, you will be offered to join another Google Classroom group where you will have access not only to the assignments, the webinars, but also to a tutor. Okay, and that's the difference between being accepted to the program and not. You will have a tutor who will mark your work and who will give you feedback, and you will have weekly tutorials with them. COMPOS COMPOS prepares you for life. We don't prepare you for exams or anything, but we give you skills that you will need to pass those exams and tricky. And we teach you problem solving, and problem solving is the thing that gets you places. I don't know how to explain that. Okay, so if you go to a Google interview, the first thing they want to know is, can you actually problem solve? They give you a problem and see how you cope with it. Right. Okay. So back to our problem. So to find the angular speed, well, we know some formulas, and one of these formulas is that the angular speed is 2 pi divided by the time period. And because we know the time period is 86,400. That's the number of seconds in a day. 80, so 1 day. The period is 1 day, which is 86,400 seconds. Okay. And so it's 2 pi divided by 86,400 seconds, which gives you 7.27 times 10 to the minus 5 radians per second. Okay. Any questions here? I hope not. I hope this is very clear. The angular speed is how many radians in 1 second, and the Earth around its axis rotates 7.27 times 10 to the minus 5 radians every second. So not a big angle, not a massive angle. Now, so we found the angular speed. Now we need the linear speed. And just looking through the list of formulas, we find a very simple formula that V is equal to omega R. Now, I would write omega R small, because you have to take into account that this point is not doing the whole circle of radius r, is rotating around a circle of radius r small. So you need to find the radius of this circle, because the points on the equator, they go around the big circle, but you are not on the equator, you're going around a smaller circle. And that smaller circle, r, from the diagram, you can directly see. So this is phi. If this angle is phi, this is the radius of the planet, the smaller radius. Well, it's going to be r cos. So it's going to be r cos phi. Yeah, r cos phi. And then you take, so radius is 6,350 kilometers multiplied by cos 60. Well, cos 60 in fact is half. So it's, without even using a calculator, I can tell you that it's 3,175. Yeah, 3,000 kilometers, which is 3.18 times 10 to the 6 meters. And now we can find this. So it's 727 times 10 to the minus 5 times 3.18 times 10 to the 6, which gives you 7.27 times 3.18 times 10, 231 meters per second. This should be approximate. So that's the linear speed. That's the linear speed. And as you can see, it's quite a lot. It's almost the speed of sound. So when you're sitting in your living room, you're actually traveling at almost the speed of sound. Well, definitely the speed of the same speed as a jet plane around the Earth's axis. And that's not even taking into account the movement of the Earth on its orbit, which is even bigger. Right, and finally we have the acceleration. Acceleration, just once again looking through the it's v equals omega r. Sorry about that. Acceleration is v squared divided by r, by the radius. So we have v squared, so it's 231 squared divided by r, which is that 3.18 times 10 to the 6. Okay, 231 squared to the 6, and the acceleration is 0.017 for two significant figures. I'm going for two significant figures here, meters per second squared. So that's a 0. So that's not a lot. And that's why you don't really feel it. Okay. You know, when you are on a really fast moving train, you don't really feel that you're in a fast moving train. You just sit there. You just sit there and nothing happens. It's only when it starts accelerating is that you feel that you're moving. The acceleration could be because the train is turning and you feel this tendency for you to lean when the train is turning, or when it's accelerating, you're being pushed into your chair, or when it's slowing down, you feel acceleration. You cannot tell if you're moving or not, but what you can tell is whether you're accelerating or not. Your speed as the planet moves around its axis is 231 meters per second. That's a lot. That's a high speed, but you don't feel it. But your acceleration is very small, is 0.017 meters, and that's why you don't really feel it. Hope that makes sense. The acceleration is directed towards the center of the circle, of the small circle you're moving around. Angular and centripetal acceleration. That's an excellent question. Okay. So in this case, the acceleration is centripetal and it's directed towards the center of the circle. Oh, here it is. Sorry, it's already written here. This is the acceleration. It's even labeled for us. Acceleration. That is centripetal acceleration. Sometimes we write it down as normal acceleration because it's normal to the direction. It's normal to the direction of the movement. Now, if the speed is changing, if you're going faster, faster, and faster all the time, let's say when you get on a merry-go-round and it starts accelerating, first you go slowly and then you go faster and faster and faster. You not only have the centripetal acceleration, which causes you to turn, but you have the acceleration along your path, which is called tangential. Tangential. Sorry, I don't know. Honestly, I don't know how to pronounce that word. Tangential acceleration, which causes you to accelerate in your movement. So it's a tau. And there's also angular acceleration, which is alpha. The angular acceleration alpha is in fact just the tangential sorry, divided by the radius of the path. So this is the link between the three accelerations that we encounter. So this is the angular acceleration, there's the tangential acceleration, and there's the normal acceleration or centripetal acceleration. So centripetal acceleration or normal acceleration. Now, the angular acceleration is the derivative of omega. It's the rate of change of omega, of angular velocity. Acceleration, the tangential acceleration, is the rate of change of speed, of linear velocity. And the normal acceleration or the centripetal acceleration is v squared divided by r. Jerk. What do you mean by jerk? Oh, okay. Yes, I see. I see what you mean. Yes. Yeah. I mean, if you take the second derivative of angular velocity, that would be the jerk, angular jerk. Um, right. Problem 2. Problem 2. A point is moving in a circular path of radius r with constant angular acceleration alpha. Find vt and at. Now, if you're unfamiliar with COMPOS, if you're new to COMPOS, when in physics, when they ask you to find v of t, that means find the velocity at any given moment in time. Basically, that means find v as a function of t and find a as a function of t as well. Okay, so let's have a circular path. We assume we start from rest. It's not stated, but that's the default. We start from rest. I've well, no, you don't have to assume it. It has to be in the question. It was in the question. I've omitted that when I was copying the question. So you start moving in a circle of radius r, and the object is accelerating with constant angular acceleration alpha. And we know the link between angular acceleration and well, there are different ways you can access that. Let's start with omega. Let's start with finding omega, and we know that omega is we know that alpha is the change of omega divided by time. In other words, the change in omega is alpha multiplied by the change in time. Now, change in omega always means the final minus initial is alpha multiplied by change in time, and change in time is just simply time. So in other words, the final omega is the initial omega plus alpha t, and initial angular velocity is 0. So in other words, omega is equal to alpha multiplied by t. Omega is the angular velocity, or angular velocity. Yes, angular velocity. Okay, so, and this is what we call omega as a function of t, is alpha multiplied by t. We also know that velocity is omega r. So omega r, and that means it's alpha t multiplied by omega, or what? Sorry. Omega r t. And that's what we were looking for. That's a function v as a function of t, which allows us to find velocity at any given time. So to find velocity at any given time t, we multiply alpha by r by t. Now, acceleration. Acceleration is tricky. So let's say after some time, the object is moving. So it's moving with velocity v. So there's normal acceleration, or centripetal acceleration. Let's put it normal acceleration. But it's also accelerating as it goes around the circle. So there's also acceleration along the path, which is the tangential acceleration. Okay. And so we find both of them. We have acceleration tangential is equal to alpha multiplied by r. And that's in the formulas, one of the formulas in the table, in the assignment. So you can find that. Also, you could prove that, which is another thing. And then you have the normal acceleration, which is v squared divided by r. So that is v squared, so it's alpha squared, r squared, t squared divided by r. So r cancels, and we get alpha squared r t squared. So this is the acceleration along the path of the object, and this is the acceleration perpendicular to the object. To find acceleration as a function of t, we use Pythagoras theorem. So if you have acceleration along the path an, and you have acceleration, a tau is along the path, an is perpendicular to the path, acceleration is like this. Now, oh yeah, so it is accelerating. So let's say it's accelerating anticlockwise, and we have a n squared plus a tau squared. Okay, I hope I don't make a mistake here. So square root an, which is alpha to the power 4, r squared t to the power 4 plus a tau is alpha squared r squared. So we take alpha and r out. So get alpha r square root of alpha squared t squared t to the power 4, plus 1. And this is at. Yeah, that's it. They're not asking us to find the direction. Okay. Right. So how well do you understand problem 2 on a scale of 1 to 10, please? Oh, good. Good. Great to hear. So here we've incorporated all types of acceleration, and hopefully, okay, look at the complex numbers so far. Okay, well, you can always go back to the recording and have a look. So once you get to it. Now, problem 3 is just a discussion question, and I really like this discussion because it's so counterintuitive. So a bus is making a sharp left turn. Describe the forces experienced by a passenger. And using that, explain the difference between centripetal and centrifugal forces. Centrifugal force, basically. Centripetal force and centrifugal force. So a bus is making a sharp left turn. And a lot of you would say that when a bus is making a sharp left turn, you experience a force to the right. That's what you feel, or at least that's what you think you feel. So let's draw the bus. There's the bus. View from the top. These are the wheels of the bus. And the wheels of the bus. Here's the driver. Here's the driver and the steering wheel. And here's you. Here's you sitting on a bench or whatever you're sitting on inside a bus. The bus is making a sharp left turn, and what you experience, or what you think you experience, is a force to the right. Which, when you think about it, makes no sense. Because how can you be experiencing a force to the right if you are turning left? According to Newton's second law, your acceleration is force divided by mass. Therefore, you experience if you're accelerating to the left, you must be experiencing a force to the left. Can somebody comment on that? Can somebody tell me what's the paradox? What's the solution to that? You can speak. Don't be shy. You can use a microphone. How can you experience a force to the right? Ooh, very good, Roma. Centrifugal force does not exist. Absolutely. Force to the right. Right. If you can experience a force to the right if you are accelerating to the left. Inertia. Yeah, yeah, all great ideas. Yeah, inertia. I'd love to know if you truly understand inertia in this scenario. Well, the truth is you're not experiencing a force to the right. There's nothing pushing you to the right. In fact, something is pushing you to the left, and that's the seat and the seat and the window. If you are leaning against the window, there's the reaction force that is pushing you to the left. The friction and the normal reaction, the lower body moves to the left because of the seat. Exactly. The lower body moves to the left because of the seat, and your head seems that your head is moving to the right. Well, it's actually not. Because if you trace the body in space, you're trying to move in a straight line. Your body is attempting to move in a straight line. It's the bus that's turning left and pushing you to the left, and your body is resisting that pushing. Your body wants to travel in a straight line, but the bus says, no, you're going left with me. And you experience a force to the left. But the sensation that you have when you're inside the bus, that you're being thrown to the right of the bus, but you're not. You're traveling in a straight line. Like if there was no friction, you would keep going on a straight line. The bus turns left and hits you from the right. So it's not that you are being thrown to the right; it's the bus being thrown to the left and hits you from the right. If that makes sense. So the centripetal force is the reaction force from and the friction force, the reaction and the friction force from the seat. That's what pushes you to the left. So this is the centripetal force. And that seems quite self-explanatory. And that's what they should teach you in school. And one thing that they don't teach you in school is centrifugal force. And they say never to use centrifugal force, and they are right. Please don't use centrifugal force when in school. You can get into trouble for using centrifugal force because it's very difficult to get get a real grip on. And if you ever use centrifugal force in an exam, they will mark you down just because that's a red flag. That's a no-no. You're not supposed to know centrifugal force until you get to university. Okay, so don't use it, but just be aware that there is such a thing. It's a non-existent force which only exists in non-inertial frames of reference. So what do you mean by that? Well, Newton's laws, Newton's first, second, and third law, they are only true in inertial frames of reference. Newton's laws are only true in inertial frames of reference. A frame of reference is what you use to measure your position against. So if I'm sitting in this room, I can measure my position relative to the wall, the door, and the bookcase. You're in a bus, your frame of reference is a bus. A frame of reference can be stationary or it could be moving. We usually choose a non-moving frame of reference. Well, at least we think it's not moving, but actually is because the Earth is moving. But an inertial frame of reference is the one that moves. Inertial frames of reference, frame of reference moves in a straight line with constant speed or is stationary. That's what we call an inertial frame of reference. So a bus moving at a constant speed is an inertial frame of reference. A non-inertial frame of reference, a non-inertial frame of reference is accelerating. And what do we have? How can an inertial frame of reference exist in an acceleratingly expanding universe? That's a great question. I mean, we say that the laws of physics, Newton's laws of physics, are accurate enough for us to use them in our everyday lives. They're not accurate enough to do quantum physics, and they're not accurate enough to do astronomy. Well, certain parts of astronomy, especially cosmology. But for the movement of planets around the sun, for the movements of buses around a bend, for constructing planes and trains and everything on Earth that moves with a reasonable speed, it's perfectly fine. Okay, so this is we just accept that Newton's laws are accurate enough for us to use them. They are not true on a small scale, and they're not true on a large scale. Well, we'll get there. We'll get to the centrifugal force. Don't worry. So what I'm trying to tell you that Newton's laws or the laws of physics in general do not work if you are in a non-inertial frame of reference. And a very simple example um, would be like this. Well, Newton's first law says that if there's no force on an object, it will not accelerate. Okay. Now let's say you put a tennis ball on the floor of a bus, and the bus applies the brakes. So you are in the frame of reference of a bus. The moment the bus starts to decelerate, it's a non-inertial frame of reference. What happens to the ball? The ball starts rolling. This ball starts accelerating relative to you. So inside a non-inertial frame of reference, the ball suddenly accelerates even though there are no forces acting on it. Therefore, so the laws of physics are not applicable. Another example, so let's say you have a pendulum and a trolley. Pendulum and a trolley. And imagine the trolley moves with the pendulum. So it accelerates. As the pendulum accelerates, the trolley accelerates. So let's say you are in the frame of reference of the trolley. In this position, the energy of the pendulum is mgh, where h is the height above the minimal position. So the energy of the pendulum is mgh. Now, as the trolley moves, as the pendulum accelerates, so does the trolley. And at the bottom, and because in the frame of reference, the ball is still stationary because the ball moves with the trolley at the same speed. Yeah, so whenever, and so the speed of the ball, so the speed of the ball is 0 here, and the speed of the ball is 0 here. So the energy of the ball is 0 because now it's lost the height, but it hasn't gained any speed in the frame of reference of the trolley. So we see that the law of conservation of energy is not applicable in a non-inertial frame of reference. Yeah, effectively, Venkat, you're asking. You're doing a direct message though. Nobody can see your messages, but yes, not always applicable. Okay. Now, do you understand this example? Please tell me. Do you understand this example on a scale of 0 to 10? Okay. Right. Yes. So in the frame of reference of the moving trolley, energy is not conserved. And going back, the bus is accelerating. It is an accelerating frame of reference. It's a non-inertial frame of reference. And in that frame of reference, there is a place, there is a thing called centrifugal force. And we say the centrifugal force is equal to minus v squared minus mv squared over r. So it's an imaginary force inside the non-inertial frame of reference that pushes you in the opposite direction from the centripetal force outside the circle. And that's that's it. And this is sometimes very useful. And when you hear a Formula One driver, they always keep saying about centrifugal force, or a airline, or an fighter pilots. They say it's centrifugal force because that's what they experience in their frame of reference, because their frame of reference is accelerating. Now, if the bus is, yeah, so let's leave it at that. So it's an imaginary force which is very useful to do calculations, certain calculations. And you have a question about the train, the problem about the train. So you can use that. You can use centrifugal force. Okay. So wrapping up, do use centrifugal force in our assignment, and please don't use it in your A levels. Okay, they really don't like it. It's like you can hear the teeth of examiners, the grinding when they read the word centrifugal. They start looking for ways to mark you down. They really don't like it. So please don't do it. Okay, problem 4. This is another of those problems where there's more maths here, and the maths looks somewhat scary in here. So you have a small puck inside a hollow sphere which rotates in around a vertical axis. So these are the problems which I've labeled them dynamics problems. Is where you is dynamics because you have to do Newton's second law effectively. Newton's second law is dynamics. Like the whole dynamics section of mechanics is Newton's second law. So here you have the mg force. Mg. There's the normal reaction force. Normal reaction force. I'm calling it N because R is usually the radius. And it says find the minimum coefficient of friction so that the puck does not slide down. So that implies that the friction force is upwards, up the slope. So it's attempting to slide down. And furthermore, it implies that the friction force is limiting. So we are at limiting friction. So the friction force is mu n. This is most of the physics in this question. Yeah, drawing this accurately and realizing that these are the three forces. Now, vertically, when you resolve the forces vertically, it's not accelerating up or down, so it's stationary. In the vertical axis, the puck is stationary. So what you need to do is you need to very accurately resolve the forces, resolve mu n. So this is alpha, and this is alpha. So you have mu n cos alpha, and that's equal to mg. Oh, plus, sorry. Life's not that simple. Plus n multiplied by sine alpha. These are the upwards forces. They're equal to the downwards forces, so mg. Now resolving left and right. Resolving left and right. Well, I prefer to say resolving right, because right is the positive. I'm choosing right as the positive direction. Resolving the forces to the right. So mass times acceleration. So Newton's laws is equal to the resultant force. So mass acceleration. So it's mass omega squared r, because acceleration, because it's moving in a circle. R is equal to the horizontal forces. So n cos alpha minus mu n sine alpha. Okay. Now r, the radius of the path, it's this radius. It's not the radius of the sphere. It's a smaller radius. So it's r cos alpha. So it's m omega squared r cos alpha equals n. Let's take n out. Cos alpha minus mu sine alpha. And this is where physics ends for this question. There's no more physics in this question. All you need to do is find mu. You have two equations, and you need to make mu the subject. So this is equation number 1. This is equation number 2. Now, if you're new to COMPOS, in physics we rarely have numbers. We usually just give you letters, and you need to give your answer in terms of those physical quantities. Now, so how to approach this? Well, let's make m the subject here. Is that a good idea? No, actually, let's make n the subject here. It doesn't really matter which way around you do it. So it's going to be mg divided by mu cos alpha plus sine alpha. This is where you need to get creative, and you substitute that into here. So m omega squared r cos alpha equals mg cos alpha minus mu sine alpha divided by mu cos alpha plus sine alpha. Now m cancels, and you're left with an expression. Now m canceling is very usual. If m doesn't cancel, r is the radius of the sphere, of the big sphere. And I won't. I'll leave the fun part, the rearrangement of this to you. I'll just give you the answer, mu, and like in your own time, cos alpha, open bracket, g minus omega squared r sine alpha divided by g sine alpha plus omega squared r cos squared alpha. Okay. So I really advise you to give it a go. So what you need to do is from here, obviously this, yeah. So do get to do it. And this is the answer. This is the answer. Don't be surprised if the answer to a question looks like this. That's how physics is done properly. Yeah, so very often you see physics questions being done in this way. Problem 5. What is the minimum speed of a simple pendulum at equilibrium? At equilibrium means at the bottom position. So when a pendulum swings, it goes through the bottom position, and the bottom position is the equilibrium or the position of maximum speed. Maximum speed. And sorry for the typos. What is the minimum speed of a simple pendulum at equilibrium? So it completes a vertical circle. Now, so basically what they are asking is how fast you need to kick a ball on a rope V so that it can go and complete a circle. And in the first case, it's a pendulum on a string and B is on a rod. It should be the other way around. I'm going to switch those, A and B. Right. Pendulum on a light rigid rod, and it's on an inextensible string. Now, the difference between a rod and a string, well, because you need some speed. Sorry, let's call it U as initial velocity U. And now if it's a rod, it can, at the top, there's no minimum speed at the top. It could just as well stop at the top. So go through the top with effectively 0 speed and then fall back down on the other side. So the velocity at the top, in this case, can be 0. If it's a string, the velocity at the top cannot be 0 because otherwise the string will become slack and it just doesn't work. What I mean by that is if we draw this position, and we draw the forces acting, the forces are mg, and n. Not n is the tension. The tension. Now, if it's a rod, the tension can go this way, but it can also go this way. With a string, it can only go one way. Effectively, tension with a rod, tension can become negative in a way. If you think that towards the center is positive, outwards is negative, so tension can be negative with a rod. With a string, it cannot. It can only be positive towards the center of the circle. So, and that's that. So with a rod, so start with A. Velocity at the top is 0. So we use the conservation of energy. And in most questions, you will need to use the conservation of energy. So 1/2 mu squared is equal to mgh. And h is equal to 2r. So mg2r. And that's it. That's all you need. So you express u, m cancels, you get 4gr, and u is equal to square root of 4gr. That's it. Okay. Do you understand the solution? On a scale of 0 to 10, please let me know. Don't be shy. If it's a 1, it's a 1. There's no shame in that. This is not an easy question. Okay. It would have to be harder. Well, now with the rope, velocity at the top, well, it's greater than 0. It's greater than 0. How much greater than 0? Well, we look at the forces. We look at the forces at the top, and we have the tension force, and we have the gravity, mg, and we know that it is accelerating downwards, and acceleration is equal to v squared divided by r. So we write Newton's second law. Understand, but never would have thought to do that. Well, that's comes with practice. Newton's second law at the top, it's accelerating downwards. So mass acceleration is the resultant force. So it's T plus mg. There are only two forces that are acting. And assuming that at the top, the rope just becomes slack, it doesn't fall, but it becomes slack. So it's limiting. It's a limiting case. If you think about a mass on a rope, and at the top position, the rope just gets tiny bit of slack, and then carries on. MA. So why am I using red all the time? So it's mv squared over r over r, the radius, is equal to t is equal to 0, equal to mg. And mass cancels as usual. No, the string does not become the string becomes slack only at the top position. At any other position, it should be taut. Yes, because the critical thing happens at the top. It's a good question. I'm thinking how to prove that strictly. Well, if you just look at you have the minimum speed at the top, and you're moving in circles, and at the top position, mg is the only force that causes you to go in circles. If I mean, there's another problem where you can find the tension at any position, and that's a very good exercise. So as a separate exercise, and this is not an easy one, find the tension, find T at any position. The position, basically find T as a function of the angle. T as a function of the angle. And something like this you will have to do with the aerosled question. Aerosled is not an easy question, but you will need to find the normal reaction force as a function of the angle, and hence the I think the aerosled is an example, right? It's not a problem. So you go through the example, look at it, and you will see that at the T is minimum at the top, and T is maximum at the bottom. And at the top, the minimum value is 0. So you want the tension at the top to be 0. And from here, you get V is equal to square root of RG. So velocity at the top is square root of RG. That's the minimum speed that you need to complete the loop safely without in a circle. Now, you use the conservation of energy. Conservation of energy. So at the bottom, you have 1/2 mu squared equals to mgh. So at the top, you have mgh plus 1/2 mv squared. So you plug everything in, 1/2 mu squared equals mgh is 2 mgr, because height is 2 double the radius, plus mv squared is also here, so it's 1/2 mrg. M cancels as usual. No surprises here. Multiply everything by 2, you get u squared is equal to 4 gr plus gr. So u is equal to square root of 5 gr. And this is very similar to the problem. What is the minimum speed of what is the minimum height from which you need to release a trolley so it completes the loop? So it's pretty much the same question. The most important thing is that at the top, this is true. Effectively, you can say that the only force that causes acceleration is mg. So acceleration is equal to g, because mg is the only force, hence it's in free fall. So at the top of the trajectory, it's in free fall. So in other words, v squared over r is equal to g. And do remember this result, because this pops up all the time. This pops up all the time. How much time do we have? Oh, these are very similar problems. And if you look at problem 6, it seems impossible at the beginning, but then you realize, oh, it's actually super easy. Yeah, I have 3 lines, 2 lines written. So what's happening here? We have a pendulum which is attached at point O. We release it. It starts falling. At this point, it hits the nail and it starts moving in a smaller radius. And we know h is 2/3 L. 2/3 L. So this radius, this small radius, let's call it R, is equal to 1/3 L. And that's L. So we need to find the speed at B. Speed at B. Speed at B. And we use a conservation of energy. So we're falling from A, we're falling through a height of h, from from zero velocity. So we have mgh is equal to 1/2 mv squared. So m cancels. We have v is equal to 2gh square root. Very simple. We will find this velocity at b using conservation of energy. Now the tension. So to find the tension, we look at the forces acting on B, on the pendulum at B. And there's the tension acting to the left, and there's the mg acting downwards. And we know that mass times the centripetal acceleration is t in this case, because that's the only force acting towards the center of the circle. So mv squared over r is equal to tension. Oh, is that it? Okay. So tension is mass. V squared is 2gh. 2gh divided by r, and r is 1/3 L. 1/3 L. And we know that h is 2/3 L, so it's m 2g 2/3 L divided by 1/3 L. L cancels, a third cancels, so it's 4 mg. 4 mg. So tension is 4 mg. A very elegant problem, but really there's not much to it. Okay, any questions? Okay. That's a good question. This is Newton's second law. Newton's second law. Newton's second law says that you have a mass acceleration is equal to the resultant force. But you have two types of acceleration. You have acceleration, mass acceleration, normal or centripetal, which is in this case is equal to the normal forces. So the velocity is this way. So normal to the velocity, there's only one force, which is t. And the tangential, I need to look it up. Tangential force, mass acceleration tangential is mg. Well, minus mg in this case because it's slowing it down. Does that make sense, Ella? Okay. Yeah, I mean, and here you can write, of course, if you want mass acceleration, full acceleration, not just the normal acceleration, then of course you would write that would be t squared plus mg squared, but there's very little use of that. Acceleration normal to the trajectory and acceleration perpendicular. Problem 7. An object is sliding along a smooth track at 10 meters per second when it reaches a curved part with radius 1 meter. Find the acceleration of the body at c. So when the body is at c, Well, first of all, it has two types of acceleration. It's accelerating backwards because it is slowing down. And this is the tangential acceleration. And it's accelerating normally. Accelerating normally, AN. Okay. And as we know, let's look at the forces. Let's look at the forces acting. There's the normal reaction force. Normal reaction force. There's no friction, it's a smooth track. And there's mg. mg. If you resolve the forces, if you resolve mg, so this is mg. So this is alpha. So alpha. This is mg cos alpha. And this is mg sine alpha. So you can write mass acceleration tangential is minus mg sine alpha, and mass acceleration normal, because the acceleration is towards the center of the circle, is okay, scholars will argue whether to put a minus here or not, because I have a direction this way. It's already, I've already indicated that it's negative, so it's kind of up to you. I I would do it without a minus in this particular case, but you might want to put a minus here. It depends on your perspective. If you okay, let's do it properly. Let's do it properly, and then you will see what I mean. We will put an x-axis in this direction, and we will put a y-axis in this direction. And what we are doing is a projection of the forces on the x and the y-axis. And in this case, it has to be negative. It has to, the tangential acceleration is backwards against the x-axis, so it's going to be negative. And the normal acceleration is normal force minus mg cos alpha. Okay, that's Newton's second law. And now we need conservation of energy. That's Newton 2, Newton's second law. And now conservation of energy. Conservation of energy. And conservation of energy is mv squared over 2. That's the kinetic energy at the bottom, is equal to m kinetic energy at the, well, let's call it u. Let's call it u. mv squared mu squared divided by 2 plus mgh. And you need to find the height above the ground, of height of point C above the ground. So you have radius, angle, theta, and you need to find h. Well, we know that this length is r cos alpha. Sorry, alpha, not theta. R cos alpha. This is h. Therefore, h is equal to r minus r cos alpha. So we use that here, and we get mv squared, because we're interested in v. V squared is equal to u squared minus 2gh. Which 2? This 2 or the mv squared over 2? That's the 2 is the it's the kinetic energy, conservation of energy. So kinetic energy at the bottom. Okay, let's write it out a little bit more clearly. So kinetic energy at the bottom is equal to kinetic energy at the top plus potential energy at the top. No, that's not centripetal force. And here I've multiplied this by 2 divided by m, so I got uv squared. So you can find v. So you can find v is equal to square root of u squared, which is 10 squared minus 2 times 10 times r minus r cos alpha. Cos alpha square root, and that gives you, because we have all the numbers, that is 9.7 meters per second, and we can use that here because the normal force is the centripetal force. Normal force is the centripetal force, so we can say that this is mv squared over r, and from here we can find oh, sorry. As a matter of fact, we don't need this. We don't really need this line. Okay, this is extra. This because we're not looking for n. We don't really need this. And what we will need is this. From here, we can see that the tangential acceleration is minus g sine alpha, which is minus g sine 45, which is minus 6.94 meters per second squared. And the normal acceleration is v squared over r. So it's 9.70 squared divided by 1, which is 94.1. 94.1 meters per second squared. And total acceleration is the square root, using Pythagoras theorem, 8 tau plus an, which is 6.94 squared plus 94.1 squared, which is 94.4 meters per second squared. Of course, approximately. Okay, and now the direction. Now the direction of the acceleration. Well, you know what? What I'll do is I will copy that, put it here, and just so when the object is here, we have a small acceleration this way. So it's 6.9, and we have 94 this way, 94 this way. So obviously, this is the total acceleration is this way. By vector addition, acceleration is this way. And we need to find the direction. Well, I'm going to define the direction from the vertical. I'm going to start the direction from the vertical. So this will be 45. This is 45 degrees. And this is the angle in question. The angle that we're looking for is this. Oh, sorry, is this. Let's call it theta. So theta, in this case, is 45 plus arctan of 94 over 94.1 over 6.94. And if you do it on a calculator, arctan is the same as tan, inverse tan. It's 131 degrees, 31 degrees to the vertical. So the answer is it's 94.4 meters per second squared at 131 degrees to the vertical. Now you have some similar problems in the task, in the assignment. And now this problem is a shorter version of the problem that is already in the assignment. So basically, it's a freebie. At this point, I should stop the recording so that people who are not here don't get to see it. But okay, I won't be cruel. This problem is in the assignment. You saw it. You probably saw it. It's when a small object falls off a sphere, and at some point it loses contact with the sphere. So your task is to find where it loses contact with the sphere. And to understand that, we will draw the forces acting. So look at in this position, the forces are as follows. There's the normal reaction force, and there's is the mg, and that's it. Mg. So we'll resolve the forces. It doesn't really matter how to resolve the forces, but in this case, you need to resolve them perpendicular and parallel to the movement. So resolving the forces down the slope. So down the slope, you have mass, acceleration. The tangential acceleration is mg sine theta. sine theta. You're now resolving the forces perpendicular in this direction because it's moving in circles. So MAN, the normal acceleration or the centripetal acceleration, is mg cos theta minus the normal reaction. And the second one we're going to work with. The first one we don't really need. We don't really need the first one. And so mass then times the normal acceleration. So mv squared over r is equal to mg cos theta minus n. So when it loses contact with the ball and starts falling in a parabola, so it moves in a circle and then moves in a parabola. When it loses contact, n becomes 0. 0 means loses contact. And that's what we're going to do. So it's mv squared over r equals mg cos theta. But now we also need the conservation of energy. So a very similar scenario. So we start with r. This is r. This is theta. R cos theta. And this is h. So it falls from height h. So mgh equal a half mv squared. So v squared is equal to 2gh, which is 2gr 1 minus cos theta. And we plug this into here. So m multiplied by 2gr 1 minus cos theta r equals mg cos theta. M cancels, g cancels, mg and r cancels. And we're left with a very simple. So 2 minus 2 cos theta equals cos theta. So cos theta equals 2/3. And theta is equal to r cos. Theta r cos 2/3, which is approximately 48 degrees. Okay. So that's that. If you look at the problem, yes. If you look at the problem, this one. The small mass starts falling, and it loses contact at this point, and this is how you find that point. So I helped you out with one of the problems. Okay, any questions? Any questions? I would probably say a few words of how the course works. So for those of you who are new to it, I'll do this in a bit. Any questions?
I had
Yeah.
one
Yep.
question. Could you go back to problem 4, all the way back to problem 4, I think it was?
Yeah. Yes.
Yeah, what, how do you get to the answer?
From here.
Yeah.
So you multiply both sides by mu cos alpha plus sine alpha. You have access to this sheet. You have access to this sheet, and you can I believe you can download it as a PDF. But if it's always there, it's not going anywhere. Any time of day and night, you can have a look. Look. So how do you do it? Well, you multiply both sides by mu cos alpha plus sine alpha. So omega squared r cos alpha multiplied by mu cos alpha plus omega squared r cos alpha sine alpha. And the right hand side is g cos alpha minus mu sine alpha minus mu g sine alpha. Then you take everything with mu to the left hand side and everything without mu to the right hand side. And I don't want to you to lose on the fun and actually getting it.
Oh, I see, yeah, sorry. So it's just basically a bit of rearranging. And then the other question I had to do with
Yeah,
that question was, now how did you get MA equals FR? That's that one.
but that's Newton's second law. Mass acceleration is the resultant force.
Yeah, but it's not sliding down, so there's no acceleration.
Well, acceleration is in the x direction. Well, you can say it's the acceleration in the x direction and the resultant force in the x direction. That's what we did. This is the acceleration in the horizontal direction. So it's accelerating sideways. The acceleration is this way. Yeah, because it's spinning at the centripetal acceleration.
Yeah, but it's not moving, so how does, like,
It's not
surely,
moving up and down, but it's moving in a horizontal circle. If it's moving in a horizontal circle, it means it's accelerating towards the center of the circle.
yeah, that's for circular motion. But I was just wondering that the question was asking us to do, like, imagine that the sphere is not smooth and you were to place an object so that it doesn't roll down. So that's,
But the sphere is spinning, is rotating.
oh,
Oh, sorry, you missed that. Yeah,
oh,
this
sorry, yeah, oh, I got,
rotating,
oh,
rotating, and
oh,
the question is, you need to stay on the sphere. Yeah.
oh, well, I really misinterpreted the problem then. Oh,
Yeah. So go over it, and if you still have questions, you can get back to me. I'll explain.
thank you.
Okay. So the course. So you are given the 2 assignments, physics and maths. So this is mostly for the new people here. Physics and maths. They will be graded. We've actually started grading them, and if you do well, you get onto the course. You get a tutor who's going to mark every single one of your 10 assignments this year. You will have uh, well, they will grade your work, they will provide feedback, and you will have tutorials, which are 90 minutes, and a webinar, which is 90 minutes as well. Now, if you don't get onto the course, if you don't get a place on our program, you will have just the webinars and the assignments. Okay, so if you wish, in your own time, you do them. You can still come visit me. You can still come to the webinars, ask questions, etc. Now, to get an understanding, so last year we accepted everyone who got an average of 50% for both assignments. Okay, so if you got 50% for physics, 50% for maths, you got accepted. If you got 40 for physics, 60 for maths, you got accepted. I don't think we accepted anyone below 40% for any of the assignments, but yeah. Exam practice problem set, yes. A-level exam practice. A-level exam practice problem sets. So last year we've done well, we didn't do A-level problems. So this year what we decided to do is take the hardest A-level problems and make an assignment out of them with examples, just as our usual COMPOS format. The answer sheet. that is a question. That's a good question. I have made some answer sheets. Okay, I will do all. Yeah, I will do answer sheets for all of the assignments, and so that you have them, that you can access them for especially for last year. We won't be giving out solution sheets though. Okay, so you'll need to discuss with your tutor how to solve problems, and keep your notes safe, yes, so you don't lose them, because we won't be giving out solutions, but we will be giving out answers to problems. Okay, hope that makes sense. Okay, so good luck, everyone. Good luck. You've got over more than a month left to do the assignment, so do it well, and see you back next week. Welcome.